the absolute and conditional convergence, that part's going to be new, but then the rest is going to be reviewing all of chapter 9. So all the tests, so you're going to get practice over the next like 3 days, trying to figure out which test to use when, that whole deal, because that's most of the battle here, right? We've talked about just in general convergence and divergence, but we can be even more specific about the type of convergence. And so it can be absolutely convergent, meaning it's always convergent regardless of the circumstances or parameters, or it can be conditionally convergent, so that's only convergent under certain sets of circumstances. Okay, this is on page 229. I remember to write the page down today. Okay. And so this part is just talking philosophy theory a little bit, right? This idea that we have many of these convergent terms have negative, or convergent series have negative terms, and they alternate, or they have some kind of pattern to them. If you take the absolute value of the series, that will eliminate the negative terms, and you would think that it might make a convergent series no longer convergent, it might diverge if you start adding positives all the time. Of course, when we talked about geometric series at the beginning, we learned that you could add positive terms infinitely, and it could still converge if those terms were getting smaller and smaller and smaller as you added them. So the thing here is that sometimes when you take the absolute value of a series, it would make it less likely to converge. And that's what we're trying to determine here. Is it more or less likely to converge if we take the absolute value of the particular series? Okay. And so what we're going to do is we're going to do that. We're going to take the absolute value of the series, and if it still converges, even after we take the absolute value of it, then we say that it is absolutely convergent. Okay. If it doesn't converge after we take the absolute value, okay, and it diverges as the absolute value but still converges without the absolute value, then we call it conditionally convergent. So essentially what we're going to be doing in these problems is we're going to start off by, if a series converges after taking the absolute value, it is also guaranteed to converge without the absolute value. So this is the kind of nice part about it, is when we set these problems up, we're going to determine if the series in absolute value converges. If it does, then we're done. And we could just say it's absolutely convergent because it will also converge without the absolute value. If it doesn't converge with the absolute value, then we have to test the original series. And if that series converges, then we say it is conditionally convergent. Okay? And we're going to go through like 2 or 3 examples today to kind of that. Did I skip a? I think maybe I did. First off, right away, do the quick nth term test. Always do that one first. Because if it diverges right away, then it diverges. Okay? Because if we take the absolute value of it and find that it diverges, that doesn't mean it could still be conditionally convergent, but if I do this nth term test, then it can't be. Because right away, if the original series is divergent, then there's no reason to test for absolute convergence, right? Because it can't. Because if it's absolutely convergent, then it's also conditionally convergent, meaning the original one. So do that one first. Do a quick check of that. Always the first one. Okay. Then this is where we get into the problem, right? Determine if the absolute value of the series converges. If it does, then you're done. It's absolutely convergent, done with the problem. So that's what I was talking about before.
Is there no middle step to see if the one before that?
Nope. Just take if the absolute value of the series converges, you are done. It is absolutely convergent. Now, if the absolute value of the series doesn't converge, now you have to test the original series. If it converges, then it's conditionally convergent. So that's the case you don't want to have happen, right? You don't want to take the absolute value and find out that it doesn't converge, because then you have extra work to do to see if it's conditionally convergent. But that's where that nth term test right at the beginning is important, because a lot of the times that'll rule it out to begin with, and you just won't have to do either steps 2 or 3. And that's really what 910 is all about. Okay. All right, for example, number 1. Now, what do we know about this series to begin with? Is it? It's alternating. I mean, this series converges, right? So the nth term test doesn't help us, right? This is not the harmonic because of that alternating term. So that's good. You're getting to a place where you're starting to recognize some of the common series, right? This is the most basic alternating series. So we know it's at minimum conditionally convergent, okay? We know that just because we're familiar with this one. So what we're going to do is we're going to test to see if it's absolutely convergent. Right? What does the absolute value do to that term? It's always positive. It eliminates the alternating part. And so it turns it into which function? It turns it into the harmonic, right? And what do we know about the harmonic? Yep, it diverges. Okay. So, definitely not absolutely convergent, because it diverges when we take the absolute value. And now we've already talked about the original series, but that's what you would have to do, right? So then you'd have to look at this one, okay? And now we're saying, okay, it's alternating, it's decreasing. We're familiar with this one now. The limit equals 0, okay? So this is conditionally convergent, because it converges without the absolute value, but it's divergent with the absolute value. So it didn't turn out the easy way, right? We didn't have the short way here. The short way would have been, this would have converged, and then I wouldn't have had to do any of this. But fortunately, we started off with a pretty easy one that we are familiar with anyway, that you've seen enough times that it feels familiar. Of the conditionally convergent types of problems that you're going to see, this is as easy as they come, right? Because there was not a lot to this, and we already recognized it was easy to tell. Sometimes they're not so easy to tell, and so that's where it gets a little trickier. But then you're going to get practice at all those other tests that we've been learning about. All right, I think I have 2 more examples I want to look at. Okay. I haven't given you too many series that have trig functions in them, but we need to start considering those a little bit and thinking about what happens over a period of time as n is growing larger, what's happening to, in this case, the cosine function, okay, or the sine function, because they're basically the same in terms of what happens to their values, right? What happens to the sine and cosine values, what goes on with them? Yeah, they fluctuate. They oscillate between -1 and 1. Okay. Of course, the nice thing here, we should do the nth term test real quick. Is the limit of this as n approaches infinity not equal to 0, or is it equal to 0? It would be equal to 0. So nth term test doesn't work here. Okay, so we go and we just start with the absolute value. And just like with the alternating series that we had on the previous problem, instead of oscillating between -1 and 1, now it's going to oscillate between 0 and 1, right? It can't be negative anymore. That absolute value rules the negative out. Okay. So we should think about what kind of function, what kind of test should we be thinking about here? Huh? P series. Why P series? 1 over n squared, right? We should compare it to 1 over n squared. Well, in order for the P series test to work, what has to be true? What is the biggest, let me ask you this, what is the biggest value that this could be? 1 over n squared. Okay, or it could be smaller than that, right? So when we compare it to the p-series, we have to make sure that the p-series is larger than this. Which test am I going toward here? Direct comparison, okay? So in this case, we're going to compare to 1 over n squared, which we know is convergent or divergent? Convergent. P is greater than 1. Okay, this p series converges because p is greater than 1. Okay. So in order for us to use the direct comparison test to determine convergence, we have to show that this is bigger than this, which it is. Okay. Now there are times when it is equal to, right? When if the cosine was equal to 1, they're equal. But most of the time it's not. And so if this converges, the larger one converges, then this one has to converge because of direct comparison test.
Wait, why does 1 over n squared converge again?
Right there to the right. Okay? So p is equal to 2, which is greater than 1, so it converges by the p-series test. Therefore, if the larger one converges, the smaller one converges based on direct comparison. Okay? Yeah, I said, you know, since n starts at 1, and we're talking about integers, you know, could cosine n ever equal 1?
Register 2 pi.
Well, is 2 pi an integer between 1 and infinity? You know what I mean? That's the thing, it's got to be an integer. And the smallest integer, the integer that n would need to be in order for this to be 1 would be 0. So yeah, I'll leave out the or equal to. It can't be. Okay? So this definitely has to be smaller than this because essentially cosine n, since it can't be 1, has to be a fraction. If I take 1 over n squared and multiply it by a fraction, it's going to be smaller than that. And so since this converges by direct comparison test. Therefore, what we can say is this whole thing is absolutely convergent. That's the whole point here. It is absolutely convergent because it converges with the absolute value. The idea is take the absolute value of the original problem. Let's see if we can determine that it converges or not. And it's going to be up to you to determine what test to use to do that, right? I know when we look at cosine, we think of this abstract idea, but let's remember what it is. It's just some value between negative 1 and 1. And so we're thinking about, again, that n squared is the giveaway. Right away, we're basically just comparing it to 1 over n squared. It's not basically, we are, right? And the key here is determining that this is always bigger. And since we pick 1 over n squared as well, because 1 over n squared, we know converges because of this over here. Okay? All right, other questions before we move on to the last one? All right, last one, number 3. This one's going to get you a little bit, I think. The e's and the n's. Remember, e is a constant. E is a number. It is not a variable. All right, so we start. And we start by just taking, well, did we do the nth term test on the other one? We did. We did. We should do the nth term test here. What do we think? Which one grows faster? The top or the bottom? So what's the value in this expression that changes? The e or the n? The n is going to change, okay? So if I take a number and I raise it to the same power, even if that number gets bigger and bigger and bigger, but I always raise it to the same power, because that's what e is. If you need to think of it as 2 or 3, fine. But I'm basically saying 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, right? That's how you want to think about it in terms of making an assessment of the value of that, do that, okay? So if I take negative 3 to some increasing power, to the second power, third power, fourth power, fifth power, sixth power, which is going to grow faster? The top or the bottom?
Is it not the top?
Are you sure?
Yeah. Well, if
100%. The top is definitely going to grow faster. No question. No, I want you to think about that. I want you to contemplate that because I think we struggle with that a little bit, right? As the exponent grows, the number grows exponentially. When we use that phrase in regular verbiage in the real world, people don't necessarily know how to use it and what it means, but when something grows exponentially, you think of the curve, right? The exponential curve. I talk about this in Algebra 2 all the time. It climbs, and then all of a sudden it shoots up. And there's your exponential growth. So because the exponent on the top is going to go to infinity, that top is going to grow crazy as compared to the bottom. All right, long story short, what are we talking about here? What is the limit as n approaches infinity for this expression? Infinity. It does not exist, infinity, unbounded, all those things. Okay? So by the nth term test, what did we just determine? It diverges. It is not equal to 0. Okay? And so then we're done. That's why you want to check the nth term test first. Because if it diverges, it can't ever be absolutely convergent. Because absolutely convergent means it's always convergent and under any conditions. But we just proved it wasn't at all. So then you can stop. That's why doing that nth term test is important.